yesterday we talked about the different parts of the scientific method: independent and dependent variable, positive and negative control groups, controlled variables. Today we're going to focus on how do we graph our data once we collect it. So first, there are two main kinds of data, and you're going to see both of these types of data in our class. The first type is qualitative data, which is descriptive data. So for example, when we are looking at the worms that we're going to be looking at hopefully next week, you may be describing the amount of movement that they have, what they look like, how big they are, etc. Quantitative data is numerical. So this is going to be the data that you're going to end up making graphs of, like the number of worms that travel to each side, or the amount of product that's being made by an enzyme or by a plant or whatever. So both of these are important. The two main kinds of graphs, keep in mind there are lots of different kinds of graphs, but the two main that you could be asked to draw yourself would be a line graph or a bar graph. So how do you know when to make a line graph versus a bar graph? A line graph is specifically going to be used if your independent and your dependent variables are both numbers. So let me give you a really good example where a line graph would be our best option. Let's say that you are going to put a plant at different temperatures, and you are going to measure the amount of oxygen that's produced. So amount of oxygen and temperatures in degrees Celsius. So you're going to have numbers here, 25 degrees, 28 degrees, and then you're going to be measuring how many milliliters of oxygen they make. So maybe they make 3.5 milliliters, 4.2 milliliters, etc. Notice how both of these are numerical. So this is going to lend itself to a line graph, not a bar. On the other hand, a bar graph is going to be used if one of your variables is not a number. Typically, one of your variables is going to be a number either way, although I guess it's possible that you could be looking at something other than numbers. So let me give you an example that would lend itself to a bar graph. So here's our data table again. This time, let's say that you were given different biomes. A biome is like an area where organisms live, such as the desert or the rainforest or the grasslands. And so let's say you were given biomes, and what you wanted to record was the amount of rainfall, let's say in centimeters per year. So notice how your rainfall is still going to be a number, but your biomes, that's not numerical. So this would be a bar graph. So that's your rule of thumb. If both of your pieces of data, your independent and your dependent variable, are both numerical, a line graph. If one of them is not, a bar graph. Somebody asked me, what about if you're doing time like years or months? Well, if it's years, what I've typically seen, so if I have year, and let's just say the number of people doing something, and it's like 1980, 1985, this is going to be a line graph. And this is 100, and this is 300, whatever. You got numbers. On the other hand, months of the year, typically what I've seen, let's say you were doing months of the year, and again, the number of people doing something. Now you have words, right? January, February. What I've usually seen is a bar graph for months of the year. I could see where somebody might get away with a line graph because technically the months of the year are chronological, so time would be progressing in order here, so it does kind of make sense that you could make a trend out of it, but I've typically seen a bar graph for that. So just a heads up, that's your rule of thumb for bar graph versus line graph. There are also what are called scatter plots. A pie chart, like if everything's out of 100%, you might see stuff broken down, in a pie chart. Scatter plots look something like this, where you have like all these dots of data. I don't think you would ever be asked to make one of these. Typically, when you get data like that, you're going to have a computer that's going to use like Excel or something, and it's going to turn that into sort of a line of best fit. That's what a scatter plot would look like. But a line and a bar are the two graphs that I would say you want to be extremely familiar with and know how to draw both. All right. More rules of graphing. The independent variable should be your x-axis, and the dependent variable should be your y-axis. So again, if we go back to our experiment here that I had with, we're doing different temperatures and the milliliters of oxygen that's made by some plant. Your x-axis is this, the temperatures. You're putting the plants at different temperatures. Your y-axis would be the milliliters of oxygen that the plants make in response to that. I would say that I can't think of an exception to this. So I would say that for the most part, whatever's on the left side of a table is going to become your x-axis. It's going to be your independent variable. If you think about it, when you do a lab and you set up a table, this is already pre-filled out, and then your data is what's going over here on the right side. So I would say I can't think of an exception to it. If you make the x-axis the left side of your table, that's going to be your independent, and the y-axis is going to be your dependent on the right side of the table. I can't imagine the scenario where you would get that wrong. Also, you will not in this class have to draw a line of best fit, but be aware that there is such a thing as a line of best fit. So for example, in a perfect world, you might get data that looks like this. Wow, it's an absolutely perfect line, and we can connect these dots, and it's a perfectly smooth line. In real life, when scientists do labs, they're probably not going to get that. They're going to get something that looks kind of like this, where it's sort of a line, but not quite. So a lot of times what you'll see, again, computers typically do this for them, is it'll sort of make a line of best fit that sort of averages out all those data points. For the purposes of our class, it is absolutely fine to connect the dots. A line of best fit tends to throw some people off. Also, keep in mind that not every graph is going to make a line anyway. The graph that you're going to be making, as a matter of fact, is going to go up and come back down. That's the one from the pretest. It doesn't make a line. Sometimes a graph might make a curve that does this, or it might make a curve that does this. So don't assume that every data collection, every data set that you collect has to make a straight line. Not all data follows a straight line. All right, so this was some practice that we did in class, so I'll run through these really quickly. What kind of graph would you make, and then what would be your x and your y axis? So let's just go through each of these. I'll just go ahead and uncover them all. Let's do what kind of graph we would make first. So we have the number of students, so that's a number, wearing polos versus spirit shirts on a particular Friday. Well, our students are a number, but polo and spirit shirts not a number, so this is going to become a bar graph. Second one, the amount of milligrams of fertilizer that make the tallest plants. And let's just assume tallness or height is going to be numerical. Maybe we're going to do meters. So this would be a line graph because our independent and dependent variable are both numbers. Next, the number of schools, so that is a number, using iPads in Broward County versus Dade County. So we're comparing counties. This is going to be a bar graph because the county is not numerical. Next, how the distance from light correlates. So distance from light, let's just assume that this is going to be meters, a number. And how does that correlate with the amount of oxygen that a plant makes? So photosynthesis, basically. So we have a number and a number. This is going to be a line graph. And our last one, the amount of products made by an enzyme, let's just say that that's going to be maybe milligrams at different pHs. A pH would be a number, 1 to 14. The amount of product is also a number, so this would also be a line graph. So that, hopefully that helps with distinguishing which type of graph you should make. Let's go back and label what should be your x and your y. So the number of students wearing polos versus spirit shirts on a particular Friday. So what are we changing? We're looking at polos versus spirit shirts. That's our x. We're measuring the number of students. That's our data. That's going to be our y. So remember, again, our x-axis is our independent variable. Our y-axis is our dependent variable, which is our data. So if you think about the data you're going to be collecting, that's always going to be your y-axis. All right, going back, the amount of milligrams of fertilizer that produce the tallest plant. So we're going to give them fertilizer and measure how tall they are. So our x-axis would be our milligrams of fertilizer. That's what we're giving them. Our y-axis would be their height. The number of schools using iPads, Broward versus Dade. So we already know the counties, Broward and Dade. That's our x-axis. Our data is going to be the number of schools we're going to go count. Next, how distance from light correlates with milligrams of oxygen. So we are going to place the plants at different distances, and then we're going to measure the amount of oxygen. So the distance from the light in this case is going to be our x-axis. We're doing that. Our data will be the amount of oxygen the plant makes in response to that. And finally, the amount of products made by an enzyme at different pHs. So we would be putting the enzyme in the pHs. So that's our x-axis, our independent variable. We would be collecting data or measuring how much product is made. So that would be our y-axis. And just to go back and give the y-axis a different color. So our dependent variable, our data, the number of students. For number 2, the height of the plants. For number 3, the number of schools. For number 4, how much oxygen the plants make. And for number 5, the amount of product that an enzyme makes. So that sort of breaks down our X and our Y, and again, whether we should use bar graphs or line graphs in each of these scenarios. All right, moving on, a few more rules. Make sure you include a title. Make sure when you label your axes, you include your units. For example, if you had here, let's say the milligrams of fertilizer that are given, and here you have the amount of oxygen the plant makes, make sure milligrams, and let's just say this was measured in milliliters, milligrams, milliliters. If you were to just put amount of fertilizer and amount of oxygen, but you didn't put the units, and the units were given to you in the table, so you have here amount of oxygen and it literally says milliliters in parentheses, they'll give you those units, and then the fertilizer, and then it literally says milligrams here. If you leave the units off, they will basically treat it like you forgot to label the axis altogether. So make sure, it's really important that you include units. As far as a title, usually there'll be a title on the table already, so just transfer the title to your graph. And the same is really true, honestly, for your labels as well. Take the entire thing that's here and put that there. And the entire thing that's here and put that there. Then you will never forget including the units. If the units are in the table, include them in your graph. The title of your table can become the title of your graph. So there's a couple of ways to make sure that you don't lose points on those things. Really important. Don't go beyond the first or last measurement. Sometimes you make a graph, and let's just say your first data point was at 6 a.m., and your last data point was at midnight. And you have all these data points in between. And you can see that the data does this. Here's 6 a.m., here's midnight. What people sometimes want to do is they want to show how smart they are and how they can clearly see that there's a trend here, that this is going to go down and this is going to go down. But if you make your line like this, you will not get the point for graphing your data correctly. And the reason why is because you are not allowed, if your solid line goes past that data point, you're implying that you have more data, and you don't. So if your first data point is 6 a.m., your line needs to start at 6 a.m. Now, it would be fine if you wanted to put 6 a.m. right here on your axis, then you could start yours right here at the intercept. That would be fine. You still would not be able to go past midnight. What you are allowed to do is make a dotted line. So you could do this. If you wanted to show that you predicted that it would continue going down here and here, you can make a dotted line. But do not continue your line past. Same thing people like to do with a straight line. If you've got a line that goes like this, a lot of people really, really badly want to just make it into an arrow and keep it going. You can't do that. If the last data point you collected is right here, then your line needs to stop right there. You could do this if you want to, but do not continue your line past the first or last measurement. If you do that, they will not give you credit for graphing the data properly. Also, a graph doesn't have to start at 0. You can make a break. So let's say your first data point's at 100. It would be ridiculous to try to start your graph at 0 and then make a scale that goes all the way to 100, and now your line is like this little tiny thing. It's silly. So what you can do is you can either just start with 100 down here, or what a very common thing people will do if their line if they want to start it much higher, is do that. Make a little break and start with 100 there. You're not allowed to make a break in the middle of your data. In other words, if your data was, say, going 100 to 500, you can't go, okay, 100, 200, break, 500. Because if you do that, it's going to obviously mess up the scale here when you graph your data. The points are not going to show the proper relationship. So you do need to, but you can make a break here. And your scales don't have to be the same on your two axes. They can be different. They should always go low to high. And the spacing needs to be proportional. So come up with a scale first. If your scale needs to get to 500, then maybe you do it in hundreds. And then maybe your scale here might be in fives, 5, 10, 15, 20. But it should be a scale. You should never see like 5, 10, 20, 50. That doesn't make any sense. You can't change midway through the distance between your numbers. So keep that in mind. All right. And basically, in the next lecture, we're going to go over this practice graph from the pretest and sort of apply all those rules that we just talked about.